Good morning, everyone. We are looking at exam 2 review for Calculus 1, covering chapter 3, differentiation rules. From section 3.1 to 3.8, here's the third part. 3.6, derivatives of the logarithmic functions. So section 3.6, derivatives of the logarithmic functions. So I'm going to start with y equals ln x. This is section 3.6, derivatives of the log and inverse trig functions. Y equals ln x. How do we differentiate that? We are going to rewrite this as e to the power of y equals x. In other words, in an exponential format. Then we differentiate both sides implicitly. The derivative of e to the power of y is itself. Remember, y is like g of x times g prime of x or y prime, and x, of course, gives you 1. So e to the power of y is itself times the derivative of the exponent. X gives you 1, y prime is 1 over e to the power of y, and as you know, 1 over e to the power of y, we can replace it with x, becomes 1 over x, meaning the derivative of y over ln x, simply write the reciprocal of the argument. So if that is the case in general, the derivative of the ln of absolute value of x is 1 over x. The reason we go with an absolute value, because remember, the domain for natural log is from 0 to infinity. Needless to say, the denominator can't be 0. If we change that to g of x, according to the chain rule, of course, we have 1 over g of x based on what we found here, and then times g prime of x by the chain rule. If we call g of x u, 1 over u du dx. And again, u must be positive. Remember the domain of a natural log, everybody. Let me remind you of logarithmic properties. Log, if b is larger than 0 and b is not equal to 1, y equals log x base b is equivalent to x equals b to the power of y. The exponent is the log, so x equals b to the power of y. That means y equals log x base b. The base is the base of the log. To make some sense out of this, I want you to look at this one and the arrow. Follow the arrow. B to the power of y is x. Follow the arrow. Again, this is something we've seen in intermediate algebra. We should have no problem with that. Okay, I'm just reminding you of that. So the general form is when y is log x base b, b to the power of y is x. And here's the properties we remember. Log 1 is 0, log b is 1. Both of them base b, of course. Log b to the power of x base b is x. B to the power of log x base b is x. Log of xy is log of x plus log of y. All of them same base b. Log of x over y is log of x minus log of y. All of them base b. And log of x to the power of n is n log x. All of them base b. And a couple of them are very straightforward if you follow this arrow. Okay. These two refer to the fact that logarithmic functions and exponential functions are inverse functions. This is called the product rule. This is called the quotient rule. This is called the power rule. When we go with common log, the base is 10. So when we see log no base, that means log x base 10. So don't write the base, means the base is 10, 10 to the power of y is x. And you can see the properties for that. I hope you can follow that. Basically, second one I want you to notice, log base b of b is 1 when the argument is called the argument of log and the base are the same. So because the base is missing, meaning the base is 10, log of 10 equals 1. Log of 10 to the power of x is x, 10 to the power of log x, and the rest of them you just don't write the base b. In the case of a natural log, the base is e. So when we write ln we mean log x base e. And that means e to the power of y is x. And you can see the general format to a specific format. ln1 is 0, ln e. This one again, number 2, the base and the argument must be the same. When we have ln, we know the base is e, so we have to put e here. Ln of e to the power of x is x, e to the power of ln x is x, and the rest of them follow. We also have the graph for exponential and logarithmic functions, more specifically base e. They are symmetric with respect to the line y equals x because they are inverse of each other. Y equals ln x and y equals e to the power of x. This is called the change of base formula. Log x base b is log x over log b with any base, for example, a. More specifically, when we don't write the base, is common log, or if we write ln is a natural log. The reason normally we use those two because calculators normally can handle those. The derivative of ln x is 1 over x. If it's ln of g of x, you flip it over times g prime of x by the chain rule. F of x equals log x base b. Then y prime is f of x 1 over x and then 1 over ln b. If the base is not e, if you recall, for the exponential, we multiply by ln b. For logarithmic, we divide by ln b. So the dx of f of x log base b of f of x is 1 over f of x times f prime of x. This is by the chain rule, 1 over ln b. This is by the change of base formula in essence. Let's start with this example. Y equals 1/2 ln of 1 plus x over 1 minus x. To differentiate this, the very first step is to use logarithmic properties to decompose this, everybody. So to decompose this is ln of the top minus ln of the bottom. So we are using the quotient rule on this part. If you don't do that, you keep the 1/2 and this one you have to flip it over according to this formula, and then you have to differentiate this using the quotient rule. But now it's a very simple case. 1/2 remains. You flip this over, you get 1 over 1 plus x. And then times the derivative of the inside, which is simply 1. Minus, you flip this over. Now times g prime of x. The derivative of the inside, now it's negative 1. So times negative 1. So what you are looking at is two fractions where the common denominator is 1 plus x times 1 minus x. So this is 1 times 1. One times 1 minus x. One times minus x. 1 times 1 minus x plus 1 times 1 plus x. So the common denominator is 1 plus x times 1 minus x, 1 times 1 minus x, and 1 times 1 plus x. Again, pretty straightforward. And we simplify the numerator as follows. This is 1 minus x plus 1 plus x. And I hope you see the numerator simply changes to 2. These two cancel each other. And we can write the denominator the way it is, or the product of 1 plus x and 1 minus x is 1 minus x squared, your choice. ln of sine theta, we want to differentiate, and number 1, we're going to flip this over according to this formula because it's ln of g of x, if you will, or g of theta in this case. Flip this over. So I'm differentiating this. I'm going to write the formula and I'm going to follow the formula from the memory. So flip this over. And then according to this, we need the derivative of sine, which is cosine. So we end up with cosine theta over sine theta. All of you know it's cotangent theta. y is equal to e to the power of x over 1 minus e to the power of x. We have to use the quotient rule, so I'm going to call this f over g. So I need f prime, which is just itself e to the power of x, times g times the denominator 1 minus e to the power of x, minus, I need g prime. I'm looking at this formula. I'm following this formula. The derivative of this one is, this is 0, minus e to the power of x. So minus e to the power of x times f e to the power of x. And you just write the denominator in the parentheses, g, and square it. All we have to do, simplify. So let's distribute. This gives us e to the power of x. This gives us minus e to the power of x plus x, or 2x. This gives us plus e to the power of 2x. Clearly, these two cancel each other. And we are done. The answer is e to the power of x over 1 minus e to the power of x quantity squared. Let's try y equals ln of 5x. Remember, this is a function, g of x first. So first you divide by it, 1 over ln of 5x. Then you want to differentiate ln of 5x. Now you need g prime of x. So what is ln of 5x? Well, flip this over, 1 over 5x, and then times the derivative of 5x, which is 5. So what happens is that this 5 cancels out this 5. The numerator remains as 1. The denominator is x times ln of 5x. And the reason we write the x in front, because we don't want anybody to think it's 5x times x, making it 5x squared, because I've seen that mistake before, that type of mistake. Let's differentiate y equals log base 3 of square root of x, and I'm writing some logarithmic properties and the derivative of natural log, where the base is e. We are very comfortable with that. So how do we differentiate that? Let me quickly show you, although we mentioned that before. So we are going to use the change of base formula for this one and write it as ln x over ln b. And that means 1 over ln b times ln x. Please understand, this is a number, everybody. It's like 5, 10, 1.8. It's some constant, some number. Therefore, if I want to differentiate this, I'm going to differentiate this, and I'm going to say this thing remains, and I'm going to flip this over, 1 over x, and therefore y prime is 1 over x ln b. So what happens here? First and foremost, this is x to the power 1/2, and 1/2 using the power rule here, everybody sits in front. So always simplify your log. So half of log x base 3. So according to this rule, 1/2 remains. Then you want to differentiate this part. Flip this over, 1 over x. You look at the base. If the base is e, we are done. And of course, that means ln. Since it's not 1 over ln of the base, 1 over ln 3, we are done. We are going to put them together as follows. 1 over 2x ln 3. The way you write this, clearly 2x is not part of the argument of log. That's why we write it in this fashion. We want to differentiate this function log base 5 of x squared plus 1. So let's see how we differentiate that. We are going to follow this methodology and add to it the chain rule. So first you're going to flip this over. Then you're going to multiply by f prime by the chain rule. Then the base is not e 1 over ln b in that order. Or you can write it as 1 over f of x ln b times f prime of x, however it works. So first we want to simplify the log. We can't. It's completely simplified. Flip it over. 1 over x squared plus 1. Flip over the argument of log. Then we need the derivative of the argument by the chain rule. So we need 2x. Then we look at the base. Since the base is not e, 1 over natural log of the base, namely 5. We are done. We just rewrite it as 2x over x squared plus 1 ln 5. Y equals ln of 5x over x squared plus 5. We want to differentiate this, again reminding you of some logarithmic properties and differentiation formulas. We're going to cut this into two parts, ln of the top minus ln of the bottom. Ln of the top becomes ln 5 plus ln x. So ln of the top, ln of 5x minus ln of the bottom. This is the quotient rule. And the top cuts into two pieces itself using the product rule, ln 5 plus ln x. Why are we writing it like this? Because I hope everybody knows ln 5 is a number. Therefore, the derivative is 0. ln x, 1 over x. Minus ln of x squared plus 5 minus, flip this over, 1 over x squared plus 5 times the derivative by the chain rule. The derivative of the argument of log is simply 2x. So what do we have here? We have x times x squared plus 5 as the common denominator. So 1 times x squared plus 5 minus 2x. Let me just... This is minus 2x, everybody, times x. Okay, we should recognize that. Now, we are going to simplify the numerator as x squared plus 5 minus 2x squared is to add up to minus x squared, and we are done. So the final answer is minus x squared plus 5 over x times x squared plus 5. G of x, log of 9 minus x cubed to the power of 4. We want to differentiate that. So we are going to use this power rule first and put the 4 in front. And now we are going to differentiate. So 4 is a constant, is a multiplier, it remains. Since we have a log, we're going to flip this over. Since this is a function of x, but not just x, we need its derivative by the chain rule. I'm looking at this part now. So 1 over f of x is 1 over 9 minus x cubed. I need f of x. The derivative of the argument of log is minus 3x squared. Finally, I look at the base. When the base is missing with log, the base is 10. 1 over natural log of the base, 1 over ln b, which is 1 over ln 10. We put them all together. 4 and 1 and negative 3x squared and 1. When we multiply all of those, the numerator becomes negative 12x squared. These two belong to the denominator. So we write 4 times negative 3x squared, negative 12x squared. over 9 minus x cubed times ln 10. We are done. We want to find an equation of a tangent line for the function y equals x squared ln x at the given pair 1 comma 0. So we need to find its slope. We need to differentiate first. To do so, I'm going to put a raised dot in between x squared and ln x. And I'm going to use the product rule of differentiation. F prime g plus g prime f. So this gives me 2x times ln x plus this gives me 1 over x times x squared. And I'm going to write at top of it that this is f prime g and this is g prime f. So this is 2x ln x, and this one is simply x plus x. Now you want to evaluate this at x equals 1 to give you this slope. So you're going to say 2 times 1 ln 1 plus 1. 2 times 1 is 2, ln 1 is 0, so the answer is 1. Y minus y1, that means y minus 0 equals m1 times x minus x sub 1, that means 1 times x minus x, 1 times x minus 1. So simply y is x minus 1. By the way, this is an x-intercept. If it were an y-intercept, 0 something, we could have used y equals mxb, but it's not, okay? We want to differentiate y equals log base 3 of 1 plus theta ln 3. And I'm going to look at it from two different points of view. Number one, I'm going to differentiate it just the way it is because I can't simplify the log further. I can decompose the log. So the very first step, according to this formula, is to flip over 1 over f of x, in this case f of theta, I would say. Flip this over. So dy d theta rather than y prime, although it is the same thing. Dy d theta is 1 over this expression, 1 over 1 plus theta ln 3 times f prime of x times f prime of theta. So let me, in fact, call this f of theta. Okay? So now I need f prime of theta. What is the derivative of this expression with respect to theta? This is 0. This is theta times some number. Please understand, ln 3 is a number, like 5. So 5 theta, the answer is 5. So the answer is times ln 3. And then we're going to divide by 1 over natural log of the base. So this means 1 over ln 3. So this part means 1 over ln 3. And f prime means ln 3. So it's pretty straightforward. So again, this is the derivative of this function. This is, what color though? This is f prime of theta. Okay. This is 1 over natural log of the base. The base is 3. So needless to say, these two cancel each other, and we end up with 1 over 1 plus theta ln 3. Now, we could have used the change of base formula in the first place. Remember, this log base 3 of 1 plus theta ln 3 is the same as ln of 1 plus theta ln 3 over ln 3. This is by the change of base formula, because I can use log of the same thing over log of 3 with any base, so I use natural log. So this is the second way. I hope you see that. Y is ln of 2 e to the power minus t sine t. We are going to differentiate this, and before that, I'm going to decompose that into 1, 2, 3 pieces, meaning ln of 2 plus ln of e to the power minus t plus ln of sine t. So cut them into 3 pieces. Notice this one, everybody, ln of e to the power minus t is simply minus t. So I hope you know that this is minus t, logarithmic properties. So one by one, we are going to differentiate y. So y prime, the derivative of ln 2, I'm going to write it that it's 0 because ln 2 is a number, and minus t is negative 1. Now ln of sine over t, we are going to flip over the sine t. We get 1 over sine t, and then we're going to multiply by the derivative of sine t, which makes it cosine t. So what we are looking at is minus 1 plus cotangent t, and that's done. T log base 3 of e to the power of sine t ln 3. We want to differentiate this. And so again, we start with simplifying the log. So this is the portion that I want you to pay attention to. And I'm going to remind you that ln of e to the power of x is x, e to the power of ln x is x, and we are going to work on that because we see the e and we see ln 3. So let's interchange these two. This is a product of these two pieces. So I'm going to put the ln 3 first. And when I do that, I put this in a parenthesis. Remember, e to the power of ln 3 to the power of sine t. This expression is the same as this expression, everybody. Let me box that. These two are identical. This expression is identical to this expression. I hope you're comfortable with that. Why are we writing it in this format? Because this, of course, e to the power of ln 3 can be replaced with number 3. Following that. So what do we have here? We have t log base 3 of 3 to the power of sine t. I hope you recognize that this simply becomes sine t, or you might write sine t log 3 base 3. This is equal to 1, everybody. So simply t sine t. So this is 1. This thing is 1, so t sine t. And now I'm going to differentiate t times sine t. So what did we have? This function. How did we simplify it? Through the process of logarithmic properties, we ended up with this. And now this requires the product rule. I'm going to call it f times g and use the product rule of differentiation. So f prime is 1 times sine t plus sine gives us cosine t times t. This is sine t. This t definitely bring it forward, t cosine t, because I don't want anybody to think this is cosine of t squared. And sometimes students make that mistake. Okay, everybody. So make sure you bring it forward. Logarithmic differentiation. And the example is y equals x to the power of 3/4 square root of x squared plus 1 times 3x plus 2 to the power of 5. In general, we use logarithmic differentiation when the function is extremely complicated. So what is logarithmic differentiation? Number one, take natural log of both sides. I'm assuming we have no problem with this process, everybody. So first, I'm going to write this as x squared plus 1 to the power of 1/2. So what is the composition of this? We have log of this plus log of this minus log of that. What is log of this? Let me write it down here and then, so we have log. So I'm taking a natural log. Let me just write natural log of y, ln of y. I have ln of the x to the power of 3/4 plus, well, I have it there for you, so I don't have to write that. So let me just actually erase this. So ln of x to the power of 3/4, ln of this minus ln of that. So that's the first step. Ln of x to the power of 3/4 plus ln of x squared plus square root of x squared plus 1, which is x squared plus 1 to the power of 1/2, minus ln of the power. This one 3/4 sits in front. This one 1/2 comes in front. This one 5 comes in front because of the power rule. This is the combination of a product and quotient rule. And now we're going to use the power rule. So 3/4 sits in front. In this case, 1/2 sits in front. In this case, minus doesn't change. 5 sits in front. It's completely decomposed. And now we are going to differentiate. When we differentiate the left side, natural log of y gives you 1 over y times, remember, this is like g of x, g prime of x, or dy dx. So 1 over y. So we're going to differentiate implicitly with respect to x. Here's the second step. So first, decomposition. So 1 over y times dy dx. This one remains the same, 3/4. And this one is 1 over x. So 3/4 doesn't change. Ln x gives you 1 over x. One half remains. Now flip this over. We are working on this one. We are working on this one. 1 over x squared plus 1. And then by the chain rule, the derivative of that, which is 2x. Okay, we're looking at this one, everybody. Minus 5 remains. 1 over 3x plus 2. And then g prime, the derivative of the inside, is number 3. So pretty straightforward, right? We are done with calculus. We are supposed to do what? Solve for dy dx, which means whatever the right side is times what? Please understand, there is a 1 over y here. So I have to multiply the y by the right side. When we multiply y by the right side, this becomes 3 over 4x. This becomes x over x squared plus 1 This becomes minus 15 over 3x plus 2. Replace the y with the given function, and you're done. And this is as complicated as it gets, everybody. It is pretty complicated, as you can see, but that's fine. All right. Y equals x to the power of sine x. The base is a function, so is the exponent, and there are two ways. You can go with the exponential rule. You can also go with the logarithmic differentiation. So to go with the logarithmic differentiation, you are going to take the natural log of both sides. So ln of this left side is ln of the right side. And the right side, sine x, will sit in front according to this power rule of logs. So sine x sits in front. And now you can see that the product rule can be used. Now we are going to differentiate both sides implicitly with respect to x, which makes this one 1 over y times y prime. The right side, we use the product rule. We need the product rule, f prime g plus g prime f. So f prime is cosine x times g, which is ln x, plus g prime, the derivative of ln x is 1 over x, times f, which is sine x. This is done. As far as calculus is concerned, it's done. And now we are going to solve for y prime or dy dx, which means we are going to multiply both sides by y. In essence, this is cosine x ln x, this is sine x over x, or 1 over x times sine x. So you multiply it by y, replace the y. Logarithmic differentiation. Derivatives of inverse trigonometric functions. The derivative of sine inverse is 1 over square root of 1 minus x squared. The derivative of tan inverse is 1 over 1 plus x squared. The derivative of secant inverse x is 1 over x squared of x squared minus 1. And actually, the rest of them just take a negative sign. So the derivative of cosine inverse is the same as sine inverse with a negative sign. So negative 1 over square root of 1 minus x squared. The derivative of cotangent inverse is the same as tan inverse, but it takes a negative sign. So notice negative 1 over 1 plus x squared. And the derivative of cosecant inverse x is the same as secant inverse, takes a negative sign, negative 1 over x times square root of x squared minus 1. So let's remind everybody of the concept of an inverse function. Y equals sine inverse of x, or sine inverse of x equals y. By definition means sine of y equals x. And remember, y is between negative pi over 2 and pi over 2. A sine inverse of sine x equals x. when x is between negative pi over 2 and pi over 2. If you recall when we discussed the inverse functions, inverse sine functions, any trigonometric functions, none of them is one-to-one unless you restrict the domain. The restriction we put on x was between negative pi over 2 and pi over 2 for the sine for it to become a one-to-one function. And of course, the range is negative 1 to 1. That's why sine inverse of x equals x when x is between negative 1 and 1, if we have it in this format. For cosine, the restriction we put was x was between 0 and pi, the first quadrant and the second quadrant. Because in the first quadrant, cosine is positive, in the second quadrant is negative. So cosine inverse of cosine x equals x if x is between 0 and pi. Cosine of cosine inverse of x is x if x is between negative 1 and 1. And here's the synopsis of everything that we have here. What I have added is, for example, for the sine inverse, if we go with sine inverse of u, what happens? We have the same formula, 1 over square root of 1 minus u squared, but by the chain rule, we tag along du dx. If you call this g of x times g prime of x. Same thing for the rest of them. For example, tan inverse, instead of x, if you have g of x times g prime of x. Or if you call it u times du dx. So I put a u here, I put a g of x here on purpose, because normally we mean that u is the same as g of x, okay? U is a function of x. All right, we are going to move on. So we discussed the derivative of inverse trigonometric functions. For example, when y is sine inverse of x, sine y equals x, and y is between the two numbers, and the derivative of sine inverse is 1 over square root of 1 minus x squared, and we are going to prove that. So let's look at the proof. Let sine inverse of x be y, this one, and by definition becomes sine y equals x. So here's the proof. Implicit differentiation. We are going to differentiate both sides implicitly with respect to x. And so this becomes cosine y times y prime or dy dx. Please understand y is a function of x. So cosine y dy dx, and x gives you 1. Therefore, dy dx is 1 divided by cosine y. Because sine y is x, remember sine squared plus cosine squared is 1, then cosine must be 1 minus sine squared under the radical. And we replace the sine with x, so 1 minus x squared. Remember, there are two answers here. Why do we keep the positive? Because y is between negative pi over 2 and pi over 2, and cosine is a positive in the fourth quadrant and the first quadrant. Cosine is positive. And so dy dx is 1 over cosine y. Replace it. That means d dx of sine inverse is 1 over square root of 1 minus x squared. We just proved that. What about tan inverse? We know tan inverse of x is y, means tan of y equals x. And Tan follows sine. In essence, the endpoints are not included because remember, those are the vertical asymptotes for y equals tan x. And so the derivative of tan inverse is 1 over 1 plus x squared. Let's prove that by differentiating this expression using this one. Tan y equals x. So we don't have to worry about that. Using, of course, implicit differentiation. Tan gives us secant squared. So this is secant squared y, dy dx, and this is 1. So again, class, tangent gives us secant squared y, dy dx, and x gives you 1. Therefore, dy dx is 1 over secant squared y. Let's go to trigonometric identities. We remember 1 plus tan squared is secant squared. So 1 plus tan squared x or y or z, anything. 1 plus tan squared y is secant squared y. So tan y is x. Therefore, 1 plus x squared is secant squared. If secant squared is 1 plus x squared, let's replace it here. Therefore, d dx of tan inverse of x is 1 plus x squared. We proved that, and I highly recommend you pick a couple more and you prove them on your own. For example, cosine or secant or cotangent, things like that. Y equals e to the power of 10x times 10 tan inverse of x. We are going to differentiate this, and I'm going to put a raised dot in between, meaning we are dealing with the product rule. So I'm going to differentiate e to the power of 10x, which is itself, by the chain rule times 10, by the product rule times 10, tan inverse, plus, now we're going to, so this class is the derivative of the first piece, this is the second piece. Now the second piece, g prime f. So this was f prime g, now g prime f. G prime tan inverse of x is 1 over 1 plus x squared, and times f e to the power of 10x. And I'm going to write at the top of it so it becomes clear that we have f prime g, g prime f. We are done with calculus. This is going to be 10 e to the power of 10x tan inverse, and this will be e to the power of 10x over 1 plus x squared. You're practically done. If you want, you can factor the common factor of e to the power of 10x, but it doesn't simplify anything. Y equals cosecant inverse of e to the power of x. And I want you to see what I wrote. For cosecant inverse is negative 1 over x squared of x squared minus 1. If we change it to u, becomes minus du dx u squared of u squared minus 1. So if we change it to g of x, it's minus 1 over g of x times square root of g of x quantity squared minus 1 times g prime of x. I hope everybody is comfortable with the concept. So what I like to do, I like to write it in this fashion. So following the fact that this is your g of x, everybody, and following the formula, what goes in here is g of x, which means e to the power of x. Same thing here. And then we need g prime. What is the derivative of g of x? Is itself e to the power of x. And notice these two are identical, they cancel each other. So we are left with this, which is minus 1 over the square root of, this is e to the power of 2x minus 1. And this is the final answer, everybody. y equals x sine inverse of 3x, and I'm going to put a raised dot in between, and we are dealing with f times g, and therefore we are using the product rule, everybody. So we need f prime, which is 1, times g, which is sine inverse of 3x. Then we need to differentiate this. And I'm going to write this so you be clear. Sine inverse of g of x, if you want to differentiate it, is 1 over square root of 1 minus x squared becomes 1 minus g of x squared times g prime of x. So we're going to write this, and I'm going to write this is the g function that we are dealing with here, okay? So what goes in here is g of x, in this case 3x. And what goes in here, g prime of x, the derivative of that, which is 3. Okay. And this whole thing is g prime, everybody, times x. So this becomes sine inverse of 3x. And this becomes 3x over the square root of 1 minus 9x squared. Pretty straightforward, everybody. I'm going to differentiate this. I'm going to put a raised dot in between. So this is a product rule. So fg. So f prime is 1. By the way, this is 1 minus x squared to the power of 1/2. We need that. So 1 times cosine inverse plus cosine inverse. The derivative is minus 1 over the square root of 1 minus x squared times x. So just write here to make sure everybody understood what happened. This is f prime g. This is g prime f. And now this minus 1/2, the same thing to the power of 1/2 minus 1, which makes it negative 1/2, the derivative of the inside minus 2x. We are done with calculus. We're going to rewrite this as follows. This is cosine inverse. This is minus x over square root of 1 minus x squared. And this one, minus and minus, is plus 2x over this one goes down, becomes 1 minus x squared to the power of positive 1/2. 2 and 2 cancel each other. So I hope you can see, this is elementary algebra, that this is equal to this. These two are opposite. The answer is dy dx is cosine inverse of x, and we are done.